All right, so we've talked extensively about how molecules are not finite things that don't move. We saw Newman projections. The bonds rotate into various conformations. And while the bonds in a cyclohexane can't rotate around freely, it can't like turn around an unlimited number of ways because it's locked into this ring, you do see that there is a lot of movement still. We can still kind of jostle this around, and because of that, there are, just like there were in Newman projections, there are more stable conformations of cyclohexanes, just like there were more stable conformations of acyclic molecules. And what this really comes down to is that a chair structure can flip from one chair to a different chair. So, for instance, this molecule here is a cyclohexane. It's a chair structure. And what happens when a chair structure flips is one of the atoms moves down like that, and the other point goes like that. So essentially, it's just a semi-rotation of a few different bonds. So what does that look like overall, I guess? So let's draw a few chair structures to show what we just showed with this model. Let's show that with two-dimensional chair structures. So we're going to draw our sets of parallel lines. So there's a molecule right there, and we're going to make it look a lot like this one here. And actually, to tell you the truth, guys, this is one of those cases where I'm pretty embarrassed about that chair. I need to go to some organic cocktail parties to practice my chair drawing. But I like that one a lot better. So we're going to stick with that right there. So what we're going to do is we're going to draw the substituents on here, like I have on this small molecule here. And what I have here is that each carbon, so this carbon here, has a reddish pink substituent and a green substituent. So what we see here is that all of the reds, red, 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 and then there's a red here, red here, red here, they're all axial. So we're going to put all the reds axial on this molecule here. So we're not even going to give them a name. They're just going to be a substituent, and they're all red axial, and then they're red axial there too. And what we also see is that all of the green substituents are equatorial. They're all going out at the equator. They're not up or down. They're east and west. They're not north and south. They're east and west. So we're going to add all of those in as the equatorial groups. So these are the equatorial substituents. So what happens when a chair flips? So let's number these carbons. So this is carbon 1, 2, 3, 4, 5, and 6. So chairs can flip, and we show it as an equilibrium because it is an equilibrium. Both chair forms could be present. But what happens when a chair flips is, if we look right now, all of the red substituents are axial. And what happens during the chair flip? Well, this corner goes down. It rotates like that. And this, what was the bottom point, rotates up. So that's what happened in a chair flip. And right now, before the chair flips, all of the axial substituents are the pink-red color. But when we flip the chair, what happened? Well, we can see now north and south here are the green. North is green, south is green, and east-west are all of the equatorial ones, and those are all pink. So it flipped. All of the green went from equatorial to axial, and vice versa. So what happened there? Well, corner 1, this carbon kind of moved down like that in the flip, and this bottom corner, corner 4, kind of moved up in the flip. So it was kind of like I'm going to do it one more time. This corner right here flipped down, and this corner flipped up. So that's what we're going to show in the next two-dimensional structure. So when that flipped down, I'm going to draw my chair out. So corner 1 flipped down. So instead of it being up here, it's now down there. So this is position 1 here. And as that flipped down, we're kind of changing our perspective a little. This is 2, 3, 4, 5, and 6. And as number 1 flipped down, this is number 1, the red that was axial is now equatorial, and the green that was equatorial is now axial. So essentially the substituents changed. So now all the reds are equatorial, and all of the greens flipped into axial positions. So that's what happens when a chair flips. All of the axial become equatorial and vice versa. So over here we had the red as the axial, and over here we have the red being equatorial. Over here we had the green equatorial, and over here now we have green being axial. So whatever was axial in one chair structure, when a flip occurs, becomes axial and vice versa. And in the next video, we're going to look at a methyl substituted cyclohexane. We'll see how this has implications in the energy of the different conformations. What else was written in there? So when chair flips, axial substituents becomes equatorial and vice versa. And if all substituents are equal in size, the two chairs are equal in energy. So here we didn't really specify if these were equal size substituents, but if they were all just hydrogens, then these two different conformations are equal in energy. So we're kind of doing the same thing that we did with Newman projections. So we looked at all the different conformations and we said, oh, this one's more stable, this one's less stable. Now we're going to do that same thing with chair structures, and we'll find that there are preferred conformations for those chair structures. And yeah, we'll see that later. Boom, boom, boom.